Good afternoon, everybody. Welcome to the continuance of Track 10. Following here, we have the Engineering Out of Digital Risk in Oil and Gas Applications, a Cyber-Informed Engineering Experience. Please help me welcome to the stage the Instrumentation and Control Engineer at Idaho National Laboratory, Mr. Benjamin Lampe.
Awesome. Testing, awesome. Okay. Well, good afternoon, everyone. So, as I mentioned, Benjamin Lampe, I'm with Idaho National Lab, and I want to introduce you to where we're headed from a cybersecurity standpoint, because what we're truly after is introducing engineering into that conversation, and really to really help us set the stage. If we consider kind of how cybersecurity has grown, right? We understand it came out of the IT space. It used a lot of those technologies, and we developed cybersecurity really focusing on the CIE triad. Confidentiality, integrity, availability as those clear security objectives that we built a lot of decisions around. The controls that we apply, the behaviors that we expect, and really how we approach mitigating digital risk. As the world of traditional cyber came into operational technology, because operational technology was adopting a lot of IT technologies, servers, computers, Windows environments, what have you, we still understood it's a world of information assurance, but we understood we needed to rethink the objectives from a prioritization standpoint. And we've often called that the AIC triad, right, where we saw availability, then followed by integrity, followed by confidentiality. But those solutions in operational technology are still built upon moving information and making operational decisions off that information. But now we've entered the world of control systems, those devices that are cyber-physical in nature. They're the ones that sit on that world and control and actuate the physical environment. And this is the world that cyber-informed engineering is built on. It's this concept that brings the engineers into thinking about controlling that digital risk in our solutions. And we started to see that only viewing that experience through traditional cyber, through information assurance, shortchanges your ability to control that digital risk. I know in our previous talk, we talked about implicit trust. There always is a reason for implicit trust between a lot of those solutions. So when that trust is abused, it leads to consequence. But we can control that consequence because we already do that as engineers in a safety context, in an operational context. And this is based on what I would say the operating objectives when designing a system. In a cyber-physical sense, we design it to the safety, performance, and reliability objectives. So why not think about those as a security objectives so that we can collaborate and coordinate our decision-making from both a governance standpoint, a compliance standpoint, but also just from a business unit to business unit conversation. And so our recommendation that we came from the lab, and we've seen a lot of effect as we've assessed a lot of private industry, critical infrastructure, is if we think about cybersecurity in light of SRP for control systems, that allows us to coordinate our decision-making, but more importantly, take credit for things that engineers are doing or can do in the physical space as compensating controls for the digital risk that's involved in the execution of our underlying systems, our control systems. So in an ONG application, right, when we think about compressor stations, they use digital technology to do that efficiently, to do that safely, and to do that reliably. Engineers, it's situational at best whether they engineer for that digital risk. But our call to arms is, as we introduce that, it caused us to introduce engineered controls as a new family of controls to control the consequence so that we can uphold safety, reliability, and performance. And that's really the foundation that cyber-informed engineering is all about. Because like I mentioned, digital technology is becoming the full expression of the space. Every piece of technology that we incorporate into these systems has a certain type of digital technology applied in it. And a perfect example was the Trice's Triton attack in Aramco, where they compromised that safety instrumented system by getting inside the memory of that controller and allowing them to overwrite and rewrite to their heart's content what was the expected operation. And from a safety perspective, that's a complete loss of that safety objective. You have no guarantees because of their ability to manipulate that memory within the safety instrumented system. And as a response, we often like to point to the key on the controller as a compensating control. Hey, just move that key into run mode, you're good. But as you start to tear down different controllers by different manufacturers, it's situational where that's truly physical, or it's just a physical appearance to a cyber solution, because that key might just affect a memory location to say if that memory location has this value, it locks the configuration. So while it may appear as a physical solution, it's still digitally realized, and that can be susceptible to cyber activity. So a key that is fully expressed physically would look at removing the write pin, for instance, where it's fundamentally, physically unable to adjust memory because of that strength of that control. And so the application of cyber-informed engineering helps us introduce that concept of allowing engineers and their expertise in the physical domain to add that into the response of our cyber activity. So it's not just cyber against cyber. Our response is truly cyber physical against cyber activity. When we think about the world of control systems, is because they have that cyber physical characteristic where OT and IT layers still just exist as an information environment. They're moving information, so you're left with information security at the end of the day for those two worlds. But the world of control systems really opens you up to this strategy. And it really explains how engineers are that missing piece in OT cybersecurity, where cyber events start in the cyber domain and adversaries seek to disrupt our information model and change it in such a way that they can lead to physical results, kinetic effects. But we can understand that as we not only applied our world of cybersecurity, but we also introduce engineered controls, we introduce additional barriers so that safety, reliability, and performance are not impacted by the combination of both these worlds. Which introduces cyber-informed engineering, which is kind of the underlying ethos in this talk, because it brings the engineers as ways to eliminate or mitigate avenues for cyber attack or the damage that it could result. There's two different ways to think about controlling that problem from a system design standpoint, but also allow the engineer's expertise to inform that. And it looks at really addressing that consequence side of our risk management paradigm. So understanding, right, information assurance is all about introducing barriers to reduce that likelihood an adversary gets to the point in the system by which to launch an adversarial command, information, some type of manipulation. But it doesn't look at controlling that effect that it has, and that's the arena that the engineers can contribute here. Just as a purview, I'm not going to go through these because it's not a CIE talk, it's an application of CIE talk. But there is 12 principles that define this worldview of what it means to be a cyber-informed engineer, right? Designing a system with that consequence focus in mind from a digital risk standpoint. And then using engineered controls as that secret sauce to control that. But if you're interested in looking at more, you can go to our website, inl.gov/CIE, and get access to all the body of knowledge. All of it's free and open source for your availability. But like I said, these principles define all the different characteristics an engineer has to control that digital risk component in our modern systems. Because we've adopted PLCs, we've adopted microcontrollers, we've adopted IT technologies nonetheless to help make our systems more efficient and operational, more connected, basically. So let's get into ONG, right? Specifically, I want to look at compressor stations because we've developed a tool here at the lab called CIE gas. It's meant to perform a CIE analysis in the context of compressor stations. But if we consider compressor stations, right, we start to see it's a system of systems inside there. And from a turbine aspect, you have turbine controls, packages that vendors bring in, like GE or what have you, come in, supply these turbines, and then you have a larger control system that orchestrates all those subsystems, let's call them. But all these are coordinated to successfully deliver that function of transporting natural gas. Because we've understood you have to pressurize that system in order to push natural gas at a sufficient volumetric rate and what have you. But as we decompose that problem, we very quickly start to understand the digital use of technology. And we understand when we use digital technology, we exchange information that represents that physical environment. And the challenge, right, as we start to modernize our approaches, the use of digital technology goes all the way down to the very last mile, where maybe in the past it stopped at the controller or stopped at some proxy device and then got translated into analog circuitry or raw signals. And then that was communicated down to other systems to act upon those raw signals. That's all being fundamentally changed by smart sensors or other sensors which now use Ethernet or TCP/IP connections to provide its signals back to a central controller or back to some type of solution that aggregates that problem and makes a calculation. But as we trace the digital effect, as an engineer, we can now respond to that, right? And in the CIE point of view, we want to start with the function in mind that we want to respond to and mitigate the effect that digital risk has, because digital risk has the possibility that the information is no longer trustworthy or it's being supplied at the wrong time. And that misalignment can have kinetic effect in our underlying systems. So if we look at, these are just some examples from the process, some of the key functions that we could have in our application. So we think about within the station control, orchestrating the overall flow that's being delivered by a set of turbines or a set of underlying systems, or we could start with the unit control. Each turbine unit has a certain scope for analysis. It's really up to an individual to decide what scope they want to do, because they can do it all, but that often comes with higher cost and time to do that type of analysis. And that's why our argument in CIE is very much if you can get the ethos into the engineer, as they're developing these systems, they can always be thinking about digital risk and not just making it operational, but also making it resilient in the event that information is compromised. So if we take a certain function here, and I took flow control, right? When we want to analyze digital risk, we often follow what I consider the control loop conversation. And it resonates with me because as a control engineer, I interpret everything through around that control loop. What are those inputs that are required to successfully deliver flow control? Where do those inputs come from? Are they communicated to me over 4 to 20 current loops? Are they communicated over me over a network communication? All those have different implications on what's susceptible to an adversarial standpoint. But as those inputs are delivered, what is the actual computations that occur? Because that computation, where does it often sit? That computation exists within the PLC controller, or it exists within a SCADA server, or it exists with maybe in a DCS solution. Understanding where that calculation exists and what's involved in that calculation helps us identify opportunities where, as an engineer, we can think about increasing its resilience. Can I change the algorithm to be more resilient? And from a safety perspective, right, we start to harvest a lot from that safety culture, right? When we think about functional safety and some of the examples that come out of like 61508 or 61511, whichever standard you might use to do that functional safety, you start seeing mechanisms like 2 out of 3 voting or redundancy or some of those to help control that safety, but ignoring the fact that the safeguard you used is on a computer, and that safeguard can be manipulated, can be changed through supply chain attacks or through false data injection. And as an engineer, if we can have that understanding up front, we can use that understanding to expand our algorithm to compensate for that, or shift some of that logic into the physical domain as a way to help control the consequence that might occur if someone was manipulating that algorithm that delivers flow control, right? If your flow control is to deliver maybe 1 million cubic feet of natural gas over a period of time, that's being informed by the flow sensors of both the inlet and the outlet to help prove that. But if those are being overwritten by an adversary, you have no way to have that assurance. So how can you get that insurance in place that's not susceptible to cyber activity if you want those guarantees in your solution? Which then from that algorithm, right, for part of the next part of that control loop is the outputs. So when that algorithm has calculated and a decision needs to be communicated, how is it communicated to the actuation elements of that system, right? Oftentimes flow control might come into the valve side of that compressor station, where it might cause the valve to want to shut to help reduce the flow or open up to expand the flow. But the results are situational, whether there's digital risk in it, right? If it's being communicated over the network to a smart valve that receives its command through a network interface that's different than a solution that uses a 4 to 20 milliamp current loop to communicate that result. But understanding that change helps us account for that risk that we use in our deciding on how that's being solutioned out. And this is all important because even in an ONG application, there's a critical infrastructure characteristic, and so we expect it to always be available, even if type behaviors, and even if is a resilient conversation, not necessarily just a security conversation, because we want to have that, even if an adversary is manipulating the control system, we still want to deliver natural gas. We don't necessarily want to recreate the Colonial Pipeline activity where they compromised not the OT system, but an information system, but it still led to shutting off the performance of the underlying control systems. Allowing cyber-informed engineering to have its way would help us restructure that so that even though they compromise that billing system, we are still, from a business standpoint, willing to deliver product because we've orchestrated that resilience so that that interdependency doesn't cause a loss of performance or safety or reliability. So you can see how those objectives start to help cross-collaborate that decision-making. But following that functional analysis, we always take that input, transform, output dynamic for each of the functions that occur in that compressor station example, which then allows us to have that consequence analysis, because kind of the principle that we see in cybersecurity, right, is you can't secure it if you don't know about it. So we want to take that functional understanding of what's involved in the input, how is it being acted upon, and how is it delivering the result. We can now question that from both the engineering perspective and the cybersecurity perspective. Because we have to understand, as an engineer, we understand the limits. We understand the timing that's allowed for, where cybersecurity may just be able to address, okay, information is present. How do I make it from being manipulated? But they don't necessarily have the example of, okay, I guess the perfect example I like to use is a Modbus, right? Where we control the coil reads, coil writes. But from a firewall perspective, what's the capability of access to? You can only say, I will not allow a command against this address, period. But that command is still allowed for a moment in time when it's necessary. But there's no aspect in the firewall to allow you to coordinate that timing of the connection, just whether it's allowed or not. But engineers can supply that understanding, so we can either improve the cyber solution or look at ways to perform those guarantees in the physical space, which from a consequence perspective allows to explore that from both parties. Which moves us into the last phase. When we think about mitigation analysis, we can take the understanding from both the engineering and the cyber and ask, how can we mitigate that? And the response will probably be, well, let's go to our NIST 853 controls and let's go select the control families that make sense to control the information that exists in our system. But we can see how that is short-sighted by the simple fact that engineers have a much bigger purview of the system and a much bigger responsibility in the system that they can help think about how I can mitigate that solution. Which comes into examples, and there's one that I wanted to highlight. There's quite a few. We've developed a pretty large database at the National Lab of examples of engineered controls. But one that comes to mind that I really resonated with was considering the voting mechanisms we might use in a compressor station algorithm to not only make it safely operate, but we can use that technique as also a cyber response. So if a sensor has been compromised and it's delivering false data, or someone has inserted them inside the middle of that channel and is manipulating that information, that sensor is no longer trustworthy. And from a safety solution, I might be able to catch that by using that voting mechanism to either discredit that sensor, so I'm not going to actually use it in the calculation. But more than that, I can cause the result to, as it says, de-energize the trip outputs. And so I can use a safety technique to remove the consequence a cyber activity might have had if that voting mechanism was not in place. Because without that voting mechanism, the sensor, let's say a flow sensor, that's being used as the input signal to the unit control or the station control to decide how much volume I need to flow through the system. If that value doesn't benefit from this resilient technique, it could cause the valve to misapply its result because the manipulation that's occurring in the controller or in the sensor being injected, if the controller doesn't have that voting mechanism applied to it as a response to the digital risk of communicating that signal over the network or in a manner that's susceptible to digital technology. And so we can see how engineers, if they involve safety techniques or they involve things that they have control over from an algorithmic standpoint or as a physical technique to eliminate that consequence. Because I'm realizing this text is very small for the other ones. But you can see how even if the solution in the controller is as simple as an if-then check, an if-else check, like if this flow rate is less than 100 CFM, let's say, that simple check could be moved to a physical logic check with using a flow switch or some mechanism to help control the consequence or provide that boundary check so that even if the controller was compromised through maintenance or through some activity, I still have a physical apparatus that provides a material science check that is coordinated with that logical check. And you can see how both then work together to, one, control the likelihood of a safety event, or I'm using like encryption or other techniques to prevent that manipulation. But even if that manipulation is checked, I still have a physical mechanism, a flow switch, that provides a harder boundary or a similar boundary to, one, either check that decision or compensate for that decision so that the worst case consequence doesn't take effect where I'm shutting the inlet valve and now I'm not moving any gas, which could be very problematic for downstream operations or other consequences that the business doesn't, could be very detrimental to the business, whether financially, operationally, or even from a health safety standpoint. And that's the benefit by introducing this world of engineered controls as a new family to information security. So it's not just cyber against cyber, it's cyber and physical against cyber effect. And that's the call to arms, that's the call to action that cyber-informed engineering is all about is, hey engineer, in this modern age, take digital risk seriously, just like you do with safety, just like you do with reliability goals that are part of your system spec. Because engineers who don't take that digital risk seriously, they'll design a solution. They'll design a DCS solution. I'll go back here. They'll design a system that will operate according to spec, but its use of digital technology leaves it susceptible to manipulation. And so they hand that over to cyber. Cyber does their cybersecurity engineering, layers in the InfoSec controls that make sense. But in the event those get compromised, either through 0 days or misconfiguration, it leaves you with the safety risk that you were already trying to account for. So if we can get in front of that and shift that conversation left so that the engineers, as they solution their system, account for that digital risk, allows them to add in some additional engineered controls to just provide those guarantees. So it's not just on cyber, and it's not just on engineering to deliver the solution, but it's that holistic cyber response that we're looking for. And that's only brought about by, one, bringing the engineer in, but even from a cyber standpoint, there's really fun conversations. And so the theory, and this is an aside, rabbit trail, if I engineer at all consequence, can I ask really strange questions like, do I care who's in the system? Do I need all this world of cybersecurity? I've limited all consequence, so by theory, I don't need a cyber stack because there's no way to create consequence. Okay, I'll draw that theory down to reality and says, as engineering are controlling consequence, even against cyber activity, and traditional cyber is making it very hard for an adversary to get to that point in time to manipulate information, you now have both compensations, especially since we know that zero trust, while it's good in spirit, is not realistic for deep control system application because you always have a level of trust that needs to be in place for the simple fact that some of the timing requirements can't deal with the overhead that zero trust would apply in that solution. Right? Encrypting this signal may disrupt its ability to maintain the latency that I need when communicating a high throughput information between a sensor and a controller, let's say, or a suite of sensors in the controller. There has to be a level of implicit trust between those two devices. And so to compensate for that, we can then introduce engineer controls to solution out those worst case consequences that we have in mind. So, so this one that I helped entertain that thought about utilizing some of that safety voting mechanism as a direct credit to engineering out cyber activity. So that even if the adversary went ham, let's say, on that sensor, that voting mechanism votes it out. So it has no effect on the outcome of that solution. So I'll stop there. Thank you. If you want to get involved, we'll have a Q&A. Feel free to reach out to our email. Question?
So,
Yeah.
Watchdogs.
Yes.
Creating a watchdog that runs a RAM to access the ROM, so that if A is not A, then the redirect and
Yes.
coils up and downs.
Yes.
And branches based on that, where would you put that? Would you create your own hardware that would go between the sensor and its ports?
Yep. So from a watchdog standpoint, one that comes to mind, and so a time delay relay has a time adherence component within the electromechanical circuitry. That time delay relay could be coordinated with that watchdog. As if you strictly want to do it on the time component, you could shift that time delay into the relay that sits outside the output of that result to help conform to that time requirements. It should be this by physical design as well, not just the software watchdog configuration. But then there's another element, as you said, the coil strategy, let's call it, within the ladder logic. Certain elements of that could be moved into physical logic elements, where I use physical logic in coordination as another safeguard to the decision tree that's being flowed through that ladder logic, or move certain NCs or NOs out of the digital into the physical, so there's a cross collaboration that the physical and the digital have to be true in order for the output to be in effect. Because what does that do? Speedometer gauge, yeah, exactly. If an adversary were to get into ladder logic and introduce new logic to bypass that, maybe insert a rung that has an always true element, so it just bypasses all that, you could have physical logic that's outside the ladder logic that prevents the execution of that output, even if it's bypassed. For that worst case consequence, because that output might be turn the motor on, full value, it might be a direct online pump. So you just get all pressure when that logic goes true. Yeah, no scram when scram does work, exactly. So there's a couple ways to think about responding to that. So as an example, yeah.
So on the cyber perspective, we often come in after the fact and bolt in all kinds of stuff.
Yes,
Go through that argument.
yes.
From a CIE perspective, do you come in after the fact? Do you have any cases where you come in after the fact that something's already engineered and include the engineering like you're explaining here?
Yep. So the one that we always train people with in a CI workshop is a booster pump station. We came into a water sector solution that was already engineered, deployed. It's been running for 5 years. There was a risk in that solution that an adversary, as they were upgrading to cloud connectivity to manage that fleet of booster pump stations, that compromising of that SCADA solution could allow them to go in and cycle the pump. Assuming that they, as part of maintenance operations, added in those logic injections that they just bypassed it. And that's where we came in with that $10 time delay relay off that output channel, so that no matter how quickly that relay card was being cycled, the effect of it never translated to the pump because the command was held in place for 10 minutes, 20 minutes within the plant dynamics, so that the pump never experienced that cycling, because our modeling proved that if we cycled anything less than 600 milliseconds, the inrush current would burn out the pump because there was no time to dissipate that heat. So that's where we retrofitted in a time delay relay off that output channel to control that effect before it hit the contactor. That's one example. Another example is on the power grid side. We think about substation control in the feeders. We're using protection relays. We introduced a second protection relay that had a different communication channel to watch for and be ANDed with the current feeder control that was used in the microprocessor-based relay type technology. So we went back to an AND operation, and that AND said, as long as you both agree, then you make the decision. But if you don't, then it's kind of a version of that voting mechanism, to be honest, but it's a 1 out of 2 voting mechanism. But it required 2 out of 2, I should have said, in order to be comfortable making that decision, because we wanted that extra resilience because the feeder off that was critical loads. from a military application. So. But the ideal goal, to your point, is engineers who are cyber informed fit that into their requirements, their design spec, and their actual design before they hand it over to cyber. Yeah.
How do you feel about the transition from some of our safety systems to start being more integrated with the DCS itself instead of the traditional model of keeping separate?
Yep.
And being able to secure those from, as you said, cyber.
Yep. So my opinion is I understand why it's happening, and I'm not in a place to stop the market because the market sees value, and I see value because it makes it more efficient in many ways. But I think it drives the cultural responses why engineer controls are such a great compensating control for the risk you're introducing from a digital risk standpoint by integrating those solutions. And especially in the context of safety, we want those guarantees. And while we can do it, we can prove out the point in information, we're always haunted by misconfiguration in 0 days. And so we always want to break that chain with some physical element. And that's the heart or ethos in that engineer control. So I think I would champion the desire to do that, but I'd also champion it knowing that I have access to engineer controls as a way to compensate for the risk I'm taking on. Yeah. Any other questions? Yeah. So my last points, we're just wrapping up our fiscal year. It ended yesterday. And so we're about ready to deliver a whole new suite of resources out of our body of knowledge, one of which is a database of engineer controls. And right now it's got about 5,500 examples in there on how engineers have applied engineering reasoning to control digital outcomes. And you'll see a lot of it benefits from that safety culture that we already use in our systems. But it's all the sectors. It goes across all the CISA, DHS-defined sectors, critical sectors. And we're growing that. We're estimating we could probably get that up to, oh gosh, probably tenfold that once we get down to the asset levels. Because that's our journey. We've looked across sectors, subsectors, but we're decomposing that problem into segments of those sectors, subsegments, and key assets within those sectors that engineer controls are used around. And as you get into the asset specific, the possibilities get really large because there's a lot of different types of assets out there. But that'll be a key resource to help really drive this cultural shift that engineers have a serious conversation to play in controlling the adoption of digital technologies as ways to be more efficient. And they are, and I think that's necessary. But we can offset it from a safety, reliability, and performance perspective, especially, as I may mention, if we can use those as our security objectives. Now we have a consistent language between the engineering community and the cyber community to make decisions that benefit each other and not just try to speak past one another or say, yeah, we need to apply this password here because compliance expects it. But the engineer argument, and I've been there before with the Navy, is, yeah, you can't put a password on there. I can't have access control because it prevents me from having a safety response. Because I have a button on my HMI that says evacuate the building. If I can't access that, I can't respond safely. And I can't have that. So I can't have these passwords. I can't. But what if someone gets in the system? I understand. But engineer controls, if I can prove those to you, I can change the conversation around compliance. And that's the cultural growth we're going through right now. And I would say we're probably 3 years into a 7-year journey to change that culture. So.
That cultural change, is it easier hurdle than, say, cyber coming into OT and saying, hey, we need all this stuff?
I believe so, just from my own experience, but I can't account for everyone's experience because I've been in that where I ran a gamma detection system that it had to be on in order for us to move nuclear fuel. Cyber come and say, we need to patch your systems. And I'm like, okay. Well, then you go tell the admiral why we're not operating, we're not moving fuel, why we've shut down, and magically, for some reason, it got exempted. It's like, but the risk didn't change. Why do we magically get exempted? And so that was cyber coming in, not accounting for the operational understanding, the engineered understanding, just operating strictly out of compliance.
But from an engineering perspective, you should have ideally had an engineer play it.
Yes. Correct. And as that cultural growth, I would have expected them to say, okay, tell me how your system would respond if an adversary were to compromise at HMI. Because they're trying to control the risk of that computer. And they didn't come in saying, okay, help me understand what you do to compensate with that if that computer was repurposed against you. And then I could have explained, hey, this HMI provides this signal, but this signal is not the only thing that's used to help adjudicate an evacuation decision. It's an element, but here is other ways I've worked into the algorithm in this other asset to compensate for a misoperation on the evacuate function, for instance. But that was never accredited for, never accounted for in that compliance aspect.
There's probably nobody there to communicate that.
Correct. And so
Or nobody asked the question.
nobody asked the question. That's the key, is nobody from that organization asked the question. And what cyber-informed engineering, if you get into the implementation guide, there's about 1,100 questions. It's an elephant. Don't eat the whole thing. Take a little bit. But it provides that language to help allow the questioning attitude to take hold so we can make better decisions. Yeah. So, those are good questions. I appreciate that. 5 minutes. Okay, we got 5 minutes.
As far as the cultural and methodology
Yeah.
sake, to actual execute it in simple lines of, hey, this is what we're going to be doing. This
Yeah.
is why we're doing it. We found a lot of success being, hey, be the asshole. Be the degenerate that hates his job and is offered $35,000 from the state to do the thing
Yeah.
that you don't want to do,
Yeah.
that you wouldn't normally do. Be the 10th man, and if this is your responsibility, how would you break it?
Yeah.
What would you do? And everyone has that. All of our automation engineers love to talk about
Yes.
how they would break it,
Yes.
what they would do about it.
Yes.
And getting them involved was a big deal as the cybersecurity architect for the firm.
Okay.
That we engage with people that can break it if they wanted to.
And I see that as a direct result because the engineers come from that safety culture where it's trained into them to have that questioning attitude, but like, you are empowered to stop this from a safety, like no matter who says it, everyone has to respond. Like if you're calling a stop order, anybody can do that if safety is involved. It's the safety culture. Cybersecurity is that new safety culture. Everyone has a role to play, even if you're the janitor at the organization. You have certain levels of access. You have the ability to cause effect. So you need to be trained in phishing and all those things that cybersecurity is becoming that new safety culture of saying, you have the ability to participate in this culture no matter what role you have, and you have the ability to be the asshole and say, no, we got to stop because we have to rethink this. Like, we've seen a lot of effect by using the SRP triad as the security objectives for the world of ICS systems. So we call that functional assurance, but that's supported by the information assurance that has elements within the control system, but it's in support of the larger goal of functional assurance because that's the ethos, that's the objectives that go cross organization. Because safety is not just an operational priority, it's now a security priority. Reliability is not just an operational priority, it's a security priority. So why not use those objectives as security objectives in your governance, in your compliance, in your way to break down this IT versus OT fight that always occurs.
Security is operational assurance.
Yes. Yeah. Awesome. Time. All right, I got the time mark. So thank you, and feel free to stay in touch.